Hello everyone, my name is Alejandro Vallajin and I'm here to present this work I did together with one of my bachelor students, Sergio Torrijos, and my PhD student, Pablo Sanchez, about discovering related users in location-based social networks. The main motivation for this work comes from the fact that neighbor-based recommender systems are very easy to understand and implement. They have been used since long time ago in the area, however they are not so frequently used in location-based social networks, where users want to check in points of interest, or POIs. We believe this is because the standard similarity metrics, like cosine or IACAR, do not capture the inherent characteristics of this domain. Because of this, in this work we propose to adapt user similarity metrics for this domain, and in particular, we study how to integrate sequentiality and geographical information into nearest neighbor recommender systems. Nearest neighbor recommendation, as most of you may already know, is one type of recommender systems. Recommender systems want to present interesting recommendations to the users. In this figure, we represent this target user in red. In order to predict the preferences of our target user, it is important to consider the preferences of the rest of the users in the system, all the users. The final goal of the system is to detect new items the user may like. When we consider all the information available in the system, we can compute which users are more similar and use those to infer the new preferences of our target user. In this example, the selected users would be the purple ones. They are called neighbors, or similar users. As you can imagine, depending on how we define when two users are similar, we could obtain different neighborhoods, which would offer us different recommendations. This is a direct consequence of the formulation used by these recommenders. It is a weighted mean that considers how close my neighbors are to me and how much they like the item. However, when we want to apply this in location-based social networks, we realize the interactions are not the same. We have no ratings, so we don't know if something is enjoyed in a positive or negative way by a user, and we ignore other signals that are very meaningful in this context: the location of the point of interest and the moment of the day at which I visited such point of interest. Because of this, in this paper we aim to integrate these two signals into novel similarity metrics. Let us consider this example, where our target user visited a museum on Sunday morning and then went to a bar and a park. Then we know that on Monday she went to a bar and park in the morning and to a restaurant in the afternoon. If we compare this behavior against the green user, we would notice that both users share most of the items in common. However, the temporal behavior is not so similar. On the other hand, if we check the behavior of the blue user, we would observe that they both tend to go to similar places around the same time, like Park D or bars A and C, or move around the same area at a given moment, like J and I, which are close to E and G. Based on this observation, we hypothesized that classical user similarities might be useful for the cases when we want to capture global preferences. However, for location-based social networks, where contextual suggestions based on the current time or location are much more important, other similarities that take these aspects into account are needed, and this is exactly what we propose in this paper. In particular, we present two similarity metrics, one based on exploiting the common check-ins but only considering those that had happened around the same time. We observe in the figure how the matching for item J would not count since they occur too far apart, whereas the one for item D would count. In this way, we exploit the temporal information. Our second similarity metric is based on exploiting how similar the trajectories followed by the users are. For this, we use well-known trajectory similarity metrics like dynamic time warping and Hausdorff distance that are more sensitive to the temporal and geographical dimensions than other metrics like the Euclidean distance. To validate this, we use data from one of the most famous location-based social networks, Foursquare. We filter the data from a dataset with 33 million check-ins and consider only those included in the city of Tokyo, resulting in around 300,000 check-ins. We then split this data into a temporal split, 6 months for training and 1 for test, and used the 4 baselines you can see here, 2 methods based on neighbors, one based on user similarities and another based on item similarities, and 2 based on matrix factorization, one that is optimized according to BPR and another that exploits the geographical influence. We use 4 metrics to analyze the performance: NDCG for accuracy, feature agreement to capture the precision in terms of how well we predict the categories instead of the items, since it is well known that this is a very hard problem due to the data being very, very sparse, and 1 novelty and diversity metric based on the inverse of popularity and the number of different items recommended, respectively. Well, so these are the first results based on accuracy. We grouped our 3 proposed approaches and UB, user-based, together because they are based on the same algorithm, a nearest neighbor recommender based on user similarities. As we can see from the table, neither user-based nor item-based recommenders are competitive against the 2 variations of matrix factorization tested, the one using geographical information getting better results. But in terms of beyond accuracy metrics like diversity and novelty, the opposite results are found. Item-based is the best method, and some of our proposed metrics help to improve the results of the user-based baseline. This result is particularly positive for the feature agreement metric, where the trajectory similarity using Hausdorff stands out. When we analyze these results in more detail, we observe that there are different types of users in location-based social networks. Those who know the city and hence explore it in a more casual way, named local users, and those that want to know the more touristic places and probably move around the same areas, which could be labeled as tourists. If we measure the performance on these 2 groups separately, the results change dramatically. While IRNMF is still the best recommender in terms of accuracy, the performance of neighbor-based recommenders improve a lot for tourists. In particular, our approach, based on temporal windows, outperforms any other method in terms of category accuracy. We believe this is a direct consequence of tourists being a more cohesive group than the general user in a location-based social network. Hence, user similarities are more useful for these cases. As an additional experiment, we wanted to check the overlap between the obtained neighborhoods by the different methods and the explicit social connections informed by the users in the system. We found that, although some of the proposed metrics obtain more explicit connections than classical metrics, this is not always translated into better accuracy. However, it might be a good indicator to improve the feature agreement, since it is always better than the baseline. To conclude, we have proposed 2 novel similarity metrics that exploit 2 important dimensions in location-based social networks, one based on temporal overlap and another based on geographical trajectories. Although the results were not positive in terms of accuracy metrics, they were competitive for beyond accuracy metrics such as novelty and diversity. In particular, they were especially positive for a subset of users identified as tourists. In the future, we aim to continue working on this, considering these promising results, and to integrate other methods from trajectory mining research, such as those methods used to process GPS trajectories, and study how to apply these techniques with check-ins coming from location-based social networks. Thank you for listening. If you want to know more or have access to the slides, code, or related research, please check our website. Thanks.